Hey folks, so today I am giving a final presentation to my graduate seminar in Stable Isotope Geochemistry. Now, the point of this presentation was to go into a topic we learned about in course and go read peer-reviewed journals on it, become something of an expert in it, and get ready to give a 30-minute lecture on the topic as our final presentation in the class instead of doing a final paper. So I chose Rayleigh distillation models, which is a thing we talked about in class a little bit, but we dealt with much more in the homeworks. And I thought it would be useful to give a more coherent explanation of these models. So if you are a chemistry student who is interested in the Rayleigh distillation modeling, this should be a very comprehensive video for you, although it does get fairly math heavy because it is a mathematical model. So, especially toward the end, but I think you benefit from listening to it all the way through. Uh, so let's talk a little bit about what Rayleigh models are actually trying to do and their history. So, distillation is an extremely old process. It's responsible for booze, the greatest thing of all, and it may be thousands of years old. So, imagine a simple situation where I just have a mixture of water and ethanol in my still, and I heat it to approximately 78 degrees, which is the approximate boiling point of ethanol. And I do this for a short time, or I do it for such a time that I'm reasonably confident there's still some ethanol left in my water. So the total amount of mass in the bottom of the still is now less because a lot of it has gone out, but it is not going out in equal measure, right? More ethanol has left than water, and surely there is some water that is left and there is some ethanol that remains. But this mass that has now less in volume now has substantially more water concentration and substantially less ethanol concentration. So I'm dealing with systems where I have a redistribution of mass and a redistribution of concentration simultaneously, and I'm interested in having a set of equations that will allow me to evaluate these complicated relationships. So, fortunately, our friend John William Strutt, the third Baron Rayleigh, whom I will call Lord Rayleigh for the rest of this discussion, is the guy who first figured out how these relationships work. Now, in today, he is best known for his work in physics, describing various waves, either in acoustics like Rayleigh waves, or in quantum physics with Rayleigh-Jean's law, or Rayleigh scattering, which is literally explaining why the sky is blue. But in his own time, he was best known for, and won the Nobel Prize for, the discovery of argon. And because he was dealing with gas chemistry, it was in that context that Lord Rayleigh developed the Rayleigh distillation models. Now, what I think is cool is that his argon lab was built into his ancestral family mansion, Turling Place, which is still the seat of the Lordship Rayleigh held by his family to this day. There is a current Lord Rayleigh out there somewhere. So this is Turling Place, and this is the coat of arms of the Barony Rayleigh. So for my classmates, this will be review, but it's still important to talk about. We have closed systems, semi-open systems, and open systems. And these are how the mass changes over time in the apparatus. So in a closed system, mass is constant. Things might be moving around, but overall the total change of mass is constant. And these tend to come up whenever you have like two reservoirs of water coming together. Semi-open systems are when mass is leaving the apparatus, but no new mass is coming in, right? So all distillation problems are, on some level, semi-open systems, and most Rayleigh models assume a semi-open system. And of course, open systems are fully open, so there can be masses coming into the system and masses going out of the system simultaneously. And so at several points during this talk, I'm going to make references to a closed Rayleigh or an open model, and those are both shorthands for a Rayleigh model that assumes an open system, assumes a closed system, etc. We do need to also talk briefly about concentrations, which will also be reviewed for my classmates. So when we're dealing with concentrations of stable isotopes, we're usually reporting them in units of delta parts per mil, which is parts per thousand, actually. And what it is it's a concentration of isotopes, well, one relative to another, that has been normed to a standard. So a delta of 0 means that the isotope concentration in this thing is exactly the same as the standard. And this is the formula for calculating it. But also, I want to talk briefly about mole fractions. So if you're familiar with general chemistry and you learned about molarity, that was the usual unit for reporting concentrations. Here we're interested in mole fractions. A lot of times in the literature we're talking about mole fractions. These are the moles of interest divided by the total number of moles. And remember, a mole is just a normed unit of mass that allows us to make calculations that match up with our stoichiometry. So the reason we do this especially is because we're dealing with gases, gas concentrations. And by the ideal gas law, if we assume a constant temperature and volume in the apparatus, then the mole fraction of our thing of interest is equal to the partial pressure of that thing divided by the total pressure, and we can measure that stuff. So we can directly go from pressures to concentrations. All right, so this is the fundamental Rayleigh law. So the final ratio of components divided by the initial ratio of components is equal to the final amount, concentration, of our component divided by the initial concentration of our component raised to the power of alpha minus 1. And here alpha is our fractionation rate, sort of our rate of relative concentration change, which we will often call F. We will often take this whole term and call it F. Now, this is the original form of the Rayleigh equation, but again, for delta notation, this is an approximate solution. It's not an exact solution. We will show that and talk about it later. Also, this is assuming a continuous removal. If we assume a removal of like all at once, then we would use this approximation and this calculation, which you may see in the literature sometimes. So, as I said, we talked about it in the homework. We talked about it a little bit. I just kind of want to recap all of that, recontextualize it, and discuss it in greater depth. So this is the classic Rayleigh, the open Rayleigh system. When you vary F from 1, that is, nothing's been removed, to 0, everything's been removed, you get these kind of curves. And so these we use for distillation, right? We can also use them for a number of other processes. In our homework, we studied precipitation from clouds as removing from the system, so we can use it to track precipitation. Now, here's an incredibly important thing. Remember how I said that this model assumes a gradual loss over the distillation? Well, this F to the A term is integrated over many small changes in concentration, and that concentration is assumed to be moving at a constant rate based on what we call the innate rate of diffusion, which is the rate of diffusion, the component of that rate of diffusion that's independent of the concentration gradient. So, some media are just thicker than others and are just harder to diffuse through, and that's what is accounted for by the innate rate of concentration. So there is an implicit time component in these calculations. So if you have some time t during the distillation process, Or if you don't like that, if you're uncomfortable with that, you know, say some concentration during the distillation process. The F, for small amounts of delta D or for small time step changes is approximately equal to 1, and that's going to be very important later on when we do some more math. So I want also to talk about this system because this system is important. We've really had a whole problem set studying this system. And actually, as I'm giving the talk, people have the deadline for turning in homework 3 hasn't come yet. So there may be some people feverishly scratching out the homework. So imagine you have a magma chamber, right? And so you've got magma that's coming up from the mantle, probably from a subduction zone. And in that chamber, it's precipitating out crystals. Minerals are crystallizing and they're being deposited on, say, the walls, probably on the bottom of the magma chamber. At the same time, though, rocks from the sides and top of the magma chamber can be melted in. So you've got mass leaving the system and mass entering the system. And we call this an AFC, or assimilation and fractional crystallization model. And so if you're just concerned with crystallization, so that's a semi-open system, no assimilation, we can use this, which is pretty similar to what we had before. But if we have both, if we have a truly open system, De Paulo gives us this differential equation. So the rate of change in the mass of the magma is equal to the rate of change in times the concentration of in minus the rate of change out times the concentration of out. It's a pretty simple differential equation. Again, if we want our solution to be in terms of deltas of stable isotope concentration, then we can use this formula with, final in the magma minus initial in the magma, initial concentration in the wall rock, and then ratio of crystallization and assimilation. And then here is our familiar friend f, and obviously this function will be undefined at r equals 1. And this is actually the equation that I'm pretty sure is the one we're supposed to be using in our problem set, so I might pause here and have someone, write it down. So we can use that to study these sorts of systems. And this is closely related to another very important system we study in geochemistry, which is, I'll talk about that in a second, which is fluid-rock interactions. So fluid-rock interactions are when you've got some underground water, let's say hydrogeology, right, and some rocks, and the water-rich fluid and the rocks are intermingling with each other, and they're exchanging isotopes. And, maybe after all that exchanging is done, then the water leaves, but you have this, closed system initially. We can use this equation to model that. But if you have small amounts of water entering and then leaving, like let's say you've got an underground river, or this is very likely to happen in geysers where you have fluid enters, gets heated up and is expelled, and more cold water replaces it, you can use this equation. And so this is a sort of common problem we're often interested in. So you've got some water-logged lithosphere being subducted. It melts into magma, and then it comes out of a subduction zone volcano where it can do what we were talking about here. And so this graph, which I forgot was in it, is my answer to problem 1 on the homework set, which is, and you really can't see it at this scale, but they all sort of start at the same, but as fractionation occurs, they tend to sort of diverge pretty wildly based on our wall rock concentration. I actually think that I don't have these units right. I think this is supposed to be 30 and that's supposed to be 10, and that's my mistake. But you can see that we're getting that same curved graph as we got before. So I just want to talk briefly about this, which we talked about incredibly briefly in class, which is the Craig-Gordon model. And this is a more complicated model that assumes that there's some of the components in the interest already in the system. So that there's already some water ethanol gas in the still before we start distilling. Or in this case, relative humidity in the air versus water that's being evaporated off the ocean. So we can account for some water already being in the air using this model. And we have to talk about alpha K and alpha EQ. So alpha K is kinetic rate of fractionation. Kinetic fractionation is physical changes. They tend to not have an equilibrium. They tend to be irreversible. So pot of water on the stove, boil it. The water is going to come out as steam at a rate much greater than what is going back in. And any isotopic fractionation that causes will not be reversible. Whereas if I put a room temperature pot of water out there, some of that water is going to evaporate and some of the water from the air is going to go in, and that's an equilibrium. So we are accounting for both rates in this equation. So let's talk now about some interesting applications of Rayleigh and where we can go from here. Obviously, there's so many things that can be done here, but I've just sort of cut it down to things I've personally found interesting, just for the sake of time. So we can estimate alpha computationally, because you'd imagine it might be kind of hard to sample those magma chambers to calculate those fractionation rates. Typically, the way we do that is by sampling igneous rock. So the magma chamber ejects lava over time, which solidifies into igneous rock, and as you go down the column, it changes, and we can use that to calculate alpha. But we can also use computational chemistry techniques to model that. Nishimura is working on open magma systems. Scott et al. Is working on fractionation that occurred during the Calvin cycle using Rubisco, and I got these graphs from him. So that from this paper, so they're estimating alphas. Here is a really cool application that I came across in my studies. It's biodegradation. So this is a semi-open system. You've got some pollution, and it's degrading, and no new pollution is being added. So our total mass of pollution is shrinking, but it's also possible, due to fractionation, that our relative concentrations of the isotopes are changing. So our authors modeled that kind of system. The authors introduce fringe degradation, which happens sort of on the periphery of the pollution mass where air can get to it and it's aerobically decomposed, whereas core degradation is degradation that occurs relatively internal to the pollution mass where it's protected from air and it just breaks down to other chemical processes. And you can see sort of the outputs of their models here. And then this is a really, really, really interesting system that, in fairness, we actually discussed in another geochemistry seminar that was held in the spring. And I'm pretty sure it was this exact paper, which is how we can use speleothems. Speleothems are stalactites and stalagmites, and there are other things found in caves. And the way these form is carbonate-rich water, usually in limestone, drips. And as it drips, it deposits those carbonates, and they build over time layer by layer. Well, we also know that delta O18 varies with climate. So we can use measures of O18 from within the speleothem column to have a proxy for climate data as we go up that column. So here we're actually linking several models together. So here's that Craig-Gordon model where water is being evaporated into a cloud. And that cloud we can model with semi-open Rayleigh as it moves. And then it precipitates into this limestone-rich valley. It goes into the groundwater. It interacts, fluid rock interactions, So some of the oxygens in that water will equilibrate with some of the oxygens in the carbonates, and then they will be deposited in the cave, and we can use it for paleoclimate. So really cool linking of models and applications. Okay, so that's the meat of my talk, but I want to spend sort of the rest of the time I have here going through a derivation of the Rayleigh model from first principles. I went back and read Rayleigh's original 1896 paper, which introduced it, and his calculus was very hand wavy, but I'm going to go through sort of point by point and let you see everything you need to know. So here are our derivations, right? X's and Y's are quantities. You can say concentrations, you can say moles. It doesn't really matter because they're all going to cancel and be unitless anyway. You have our final ratio, our initial ratio, and our F, our fractionation ratio of one component to another. What is interesting, though, is mu, nu, and alpha. So mu and nu, again, these are the innate constant rates of diffusion of the medium based on the concentrations. And these don't change with concentration gradients. They're basically proportionality coefficients. And then alpha is the ratio of the two, and that tells us the fractionation rate. So our first goal is going to be to derive the classic version of the formula, and then the second goal will be to derive the approximate solution for the delta O18, or the delta notations generally. And we can use this conversion factor to go from one to the other. So here is Raleigh's insight. He says, assume that the rate of the change in concentration of one component relative to the other is equal to the ratios of the time change for each, which is related to the innate rates of diffusion times the concentration. So dy dx is equal to dy dt divided by dx dt, which is equal to mu y over mu x. So now let's do some calculus. This is a pretty simple differential equation, separable differential equation problem. So all we do is get our y's on this side, our x's on this side, our dy's on this side, our dx's on this side, get like terms on each side, and then we're going to integrate. Now remember, a couple quick rules of integration. We can pull constants out. The integral of 1 over x is the natural log of x, and we're going to have constants of integration on both sides, but because they're arbitrary, we can really, move them around as we see fit. So when you churn through the calculus, you get 1 over nu natural log of y is equal to 1 over mu natural log of x plus c, with me having combined both arbitrary constants from both sides. So that's the calculus done. Now we want to churn through some algebra to simplify. Now there's a lot of exponent-based algebra in this proof, so these are the rules of exponents we'll need to walk our way through the proof, and I have the numbers bracketed elsewhere. So let's start by raising e, which is Euler's constant, which is approximately equal to 2.718, to the powers of both sides. We can use rule 3 and the arbitrariness of integration constants to reorganize our equation into something that looks like this. So the left and the right. Now we can cancel the e's and the natural logs using rule 1, and we can raise our remaining variables to their constant terms, which is why I've kind of written it like that. So we get the form y to the 1 over nu power is equal to c times x to the 1 over mu power. Now to get y by itself, all we do is raise both sides to the nu power and simplify using rule 2. So now we can bring in those ratios we've been so interested in. We were interested in the ratio of y to x at some time, usually the end of the distillation process. So let's divide both sides by x using rule 4. And if this is true at any part during the process, then it should be true for the initial ratio as well. And if our interest is in the final ratio divided by the initial ratio, then all I have to do is take this, divide it by this. The c's will cancel, and the exponents will simplify by exponent rule 5, and I'll have that. So that's pretty close. Now all we have to do is put in our substitutions, and there we go. We have proved from first principles the original version of the Rayleigh equation. Now, all we have to do is express this in delta notation, and we're done. So again, remember, we're going to use this f substitution here to get rid of this x over x naught. And we're going to use our conversion factor that we talked about before. The algebra here is so simple, I'm not even going to churn through it. But you can prove for yourself that this is the end product of that algebra. Now that's a little bit interesting. But remember, we had this discussion about how, f is going to be really close to 1 for any small value. So we can sort of treat this as 1, and 1 to any power is 1. So we can sort of get rid of this. And then we have our final approximation, which was our second goal, QED. Now normally I'd ask questions here, but since I don't have time, please feel free to put questions in the comments. Here are my peer-reviewed journal sources. Here are my non-peer-reviewed journal sources, mostly lecture notes and textbooks. And thank you for my talk. This has been fun, and have a fun end to the rest of your semester. Take care, folks.